Hello everyone. Today we're going to be doing the chemistry and the intro to chemistry and the diversity of materials in the environment. These are the topics I'm going to be covering for today. I've already covered three of these, but I didn't got the video out in time, and I figured out I might as well put these clips to good use. And I'll combine it here as well. So let's start. What is chemistry? And chemistry is a central science. So, chemistry is just basically the study of matter, its composition, structure, properties, and changes. And as we could see in this diagram below, we have earth science, it's how the earth and universe was formed, physical science, which is the structure of matter, and the study of life, which is biology. And as the name suggests, chemistry is the center science over here with this red circle here. It's just the study of everything. It combines everything from these three fields, not just three fields, but every other field of science, and then it just studies matters, composition, structure, and changes. That's really it for this first pointer here. So when you're asked what is chemistry, it's just a study of matter and how it undergoes. It's just all the properties of matter. That's one down already. So next is branches of chemistry. We have a total of 8 I've listed here. So let's start with analytical chemistry. It's the properties of chemical compounds and composition of compounds and mixtures. So you can use this in quality control because they take a look at all the compositions and let's see if it passes the standards, as well as food nutrients. So that's nutrition facts, and like the nutrition facts you see at the back of food packages, that's related to analytical chemistry. They gather a lot of data, they analyze it, they make sure it's under quality control, and all the information is right. For organic chemistry, it's actually substances containing carbon and hydrogen and combined with other atoms such as oxygen, nitrogen, and sulfur. So it may sound a bit complex, but it's really just the pills, like medicines we use, the pills, and plastics, really. It's plastics is considered here, but we have another separate topic for not real topic but branch for plastics. But that falls under organic if we're dealing with pills. Next is inorganic. This is the ones without any carbon-carbon bonds. And really, there's only one type of place we can find this, and that's mining or semiconductors. Because here we don't deal with any carbon at all. It's really inorganic. Physical chemistry is just studies the physical properties, as we could see. It involves the chemical processes in terms of physical properties of matter. So if you've ever seen those chain reaction machines, those are an example of physical chemistry right there. How about biochemistry? It's the name suggests it's just concerned with the chemical processes of living organisms. It's or we could consider that as crops. Crops are considered living organisms as well. They're plants. That's why we have fermentation and nutrition as our application. Afterwards, we can move to environmental chemistry. This is just the interaction of matter and the environment, and it's just pollution. So we have the matter that we pump out into the environment. That's just environmental chemistry. That's why we have pollution. Next is the plastics, polymer chemistry. It's just the study of plastic and other chain-like molecules that are like smaller molecules but bonded together. It's really just plastics is the best example here. And lastly, but not the least, is thermochemistry. It's concerned on how heat is involved in chemical processes. So the best example here is our refineries. And with all of that stated, really, this is the 8 branches of chemistry that we can take note of. There are probably a few more, but these are the ones that I know of, and that's basically it for branches of chemistry. We can take that off our list. All right, just give me a few minutes or so to set up for the next topic. So the next topic we're going to be going through is the scientific investigation. What is it? It's a systematic approach of studying phenomenon or solving a problem. You communicate the results to the community afterwards, and it involves something called the scientific method. The scientific method is a way to prove or disprove or credit someone's work, or just to see if your hypothesis is correct. So that's actually an 8-step process. We have an observation, we ask questions, we do research, formulate a hypothesis, test the hypothesis, record data, conclusion, and communicate results. So I'm going to illustrate it right here, where let's say you notice a change in melting time for the ice when you applied salt on it. So step one is obviously our observation. So let's say you are in a lab. So this is you, and then you. We have a table here with 2 beakers or 2 ice cubes. So you realize this one has salt. So let's just put some gray stuff here. So you realize this is you, and you realize that the ice seems to melt faster, or there's a change in melting time when you observe the one with salt versus the one with no salt. So that's your observation there. Afterwards, you ask yourself a question. So let me just redraw this one again. And then you have yourself just asking a question here. So, I mean, what else do you think? Like, do you think this is the phase where you ask yourself, what happens? What's the effect of ice when melting something? When melting, what's the effect of salt when melting ice? Does it go faster? Does it go slower? Does it have no effect at all? This is the phase where you start to ask yourself these questions. And then on the third step, you realize you do first some research. So you go to your desk, and then you go on your like laptop or PC, and then you research about it. So and then you see these articles and stuff with like you see these articles about what is the effect on salt and on ice, or the melting time of ice. And then you go to your drawing board here, and then you make up something called a hypothesis. What is a hypothesis? So let's just draw that as well. So a hypothesis is what you think will happen during your experiment. Well, it has a few rules. It only has one rule, really. It has a universal rule of being in an if-then statement. So what does it mean? So if something happens, this will happen. But it also must be measurable and specific. So in this scenario, we are gonna do, if salt is applied on ice, the melting time has an effect. This is a wrong hypothesis because what is the effect in question? Does it melt faster, melt slower? Does it have no change? We don't know. And in scientific investigation, we have to be specific. That's why the correct way to make a hypothesis is something like this. If salt is applied on ice, the melting time shortens by 5 seconds. Now we have something to rely upon because shortens by 5 seconds is specific, and we can ask ourselves specifically if it's true or false, unlike has an effect, which is more vague. So back to our illustration over here, we're going to test your hypothesis now on the same desk. So you got your desk here, and then let's put testing. And then you have 2 beakers of the same conditions. Then in this case, you're going to now put your ice in both beakers or both containers, and then you just sprinkle a bit of salt on the other one. And then afterwards, you go here, data room. Let's put data room here. After you analyze the experiment, you go back to your drafting room, let's say that, and then you put no salt versus with salt. Sorry. Sorry for my bad drawings here. I'm just trying to illustrate the, yeah. So let's say, okay, so now you go back to your data room, and let's put 10 seconds, for example, and you say 5 seconds here for the melting time. And then this is where you also reject, oh, well, not yet, but you just gather data first. And then conclusion. So the conclusion is the 7th step in the scientific method. And now you go back to your hypothesis. Then we just draw that again. Hypothesis. And we just draw some of this. Correct in this case. So just a reminder that your hypothesis can be either accepted or rejected. And then lastly, we're going to communicate the results. So, this is you. And then you just tell them what happened, like this. And then you have your other friends here, or your other group mates here. You tell them about the scientific method and what you did. So this is just a rough this is just a rough sketch of the scientific method, as we could see here. So yeah, that's just basically the scientific method. And when you're doing the scientific method, you'll encounter 3 types of variables. Independent, the variable that's being changed. Dependent, it's the result of the independent variable, and it relies and it's dependent on the independent variable, because without it, it cannot exist. And controlled is just the variables that are not really related to the experiment, or they're just there really. So let's use our salt experiment, for example. So our independent variable would be, in this case, the amount of salt. Why? Because based on our hypothesis, we need to add salt, and we were going to add salt, and apparently it will change the melting time, and that's why we use that as our independent variable. How about the dependent variable? It's the time of the ice melts. Let me just write that down. So why is this the dependent variable? It's because the time of the ice melting is dependent on the amount of salt. So it relies on this, so that it's either going to be faster or slower. And then what are the controlled variables? Well, they're not really stated here, but we could consider the type of water, dirty or clean, maybe. Or we could consider the temperature of water. That's also a possibility. And that's just another scenario of the scientific investigation here. It's really it's a pretty nice process, and I think we can use this in our everyday lives. And thus, that's our 3rd topic done. Alright, the next one is a pretty complex one. It's the mathematical skills in chemistry. I've managed to list down 3 so far, and there is one last topic we will discuss under this unit, but let's finish it first. These 3 first. So in significant figures, there are actually 3 types of numbers. These are the counting numbers, defined numbers, and measured numbers. Counting numbers are like 1, 2, 3. These are numbers you use to count stuff. 4, 5. It's any integer greater than 0. Meanwhile, what are defined numbers? Defined numbers are words substituted for numbers. For example, you can just say 1 dozen instead of 12. And measured numbers are just measured using estimates. So let's say you see a line with 30 between, let's say you have a beaker here, and then you have 36 and 35. However, the water only goes until, let's say, here. You can say that this is 35.5. This is the number, and this is your estimate. These values are never exact, and That's why we call them measurements. How about what are actually rules of significant figures? There's 5, and I will show you how each one works in this application. So let's read rule number 1 first. I'm not gonna rewrite the rule, but rule 1 states that all non-zero digits are significant, which means numbers such as 324 grams, let's say 47 liters, or 70 let's say 72 yards or kilometers. So let's count each digit, shall we? So 1, 2, 3, that's 3 SFs. 1, 2, that's 2 SF. And 1, 2, that is 2 SF. So the rule number 1 is just a fundamental rule. How about rule number 2? Hold on. Rule 2 states that zeros on the left are placeholder zeros and are not significant. What we mean on the left, it's actually the left of the first non-zero number. So these are usually only just in like really small numbers, such as this one. Let's say 0.297 grams. And these are not significant, okay? These 4 zeros not significant. So you only count starting here. 1, 2, 3. So this one has 3 SFs. How about rule 3? Zeros between non-zero digits are significant. So for example, 7,003 kilometers is actually 4 SFs because these 2 zeros here are in between 2 non-zeros, 7 and 3. That's why we have 4 SF. Running out of space here, so I'm just going to expand it here. Sorry. Anyway, rule 4. Rule 4 states that zeros following non-zero digits on the right of the decimal point are significant. So we have 0.024. So this has 2 significant figures because of another rule. That's rule 2. However, 0.2400 has 4 significant figures because, as we stated, these zeros on the right of the decimal point, yep, these are the right of the decimal point, and make sure it follows a non-zero. So these 2 are counted because this is a non-zero, and this one is not counted. So this is 4 significant figures. Rule 5 is probably the most complex of all, but yeah, it's pretty self-explanatory. Let's ask ourselves, how many SFs are in 22,000 meters? Let's say that. You might say 5, 4, 3, or 2, depending on how much it's rounded off to. It's only 5 significant figures if you're counting from the ones digit place. So when the question asks, how many significant figures are here? If rounded to the ones place, you count from the ones, and then 2, 3, 4, and 5. So there's 5. However, if it says count from the tens or rounded to the nearest tens, it has 4. So tens place, hundreds, thousands, 10,000s. So only 4. And then if it has hundreds place only, it's 3. Because hundreds, thousands, 10,000s. You get the point. So it can have 2 to 5 SFs. So that's significant figures. It's very self-explanatory, but it's important in our calculations later. Scientific notation. This is used to express large numbers in this format. So A, such that A is between 1 or 10. However, it cannot be lower than 1, so 0.99 doesn't count. And it cannot be 10 as well, because 10 doesn't count. So 9.99 is probably the max value. And n is the amount of places a decimal point moves. It depends if it's positive or negative. If it's positive, we have to move the decimal point to the left. So as you can see in our 210, it became 2.1 times 10 raised to 2 because we moved the decimal point 2 spaces to the left. Meanwhile, if it's a negative exponent, the decimal places move to the right, as we could see. So from 0.021, it became 2.1 times 10 raised to negative 2, which is here visualized. As you can see, 2 places to the right. Now we know how to convert. Let's convert some from standard notation to scientific notation later. Let's see how about scientific to standard notation. It's basically this but reverse. So this time, 2.1 times 10 raised to 2 is 210. We move if the exponent is positive, we move it to the right, as we can see over here. 2 points to the right. Similarly, when we're dealing with a negative exponent, we move it to the left. So 2.1 times 10 raised to negative 2 is 0.021, as we could see over here. So let's apply this, shall we? If you're given 573,000, and we need to change this to scientific notation. Let's figure it out. So we're gonna put a red point here. Okay, that's because that's where the decimal point is. And then we want to let's pretend to hide the numbers. So we're going to keep moving this point until the number is between 1 and 10. So 1, 2, 3. So it's now 573. 4, 5. So now it's 5.73. So our new point will be here. Therefore, it's 5.73 times 10 raised to 5 because we moved our decimal point 5 spaces to the left, as we could see over here based on this rule. Now let's try a negative exponent, for example. How about 0.00035? Once again, we're going to move this decimal point to the right this time until we get a number smaller than in between 1 and 10. So we go 1, 2, 3, and 4. So now we have 3.5. So we just put 3.5 times 10 raised to negative 4 because we moved the space to the right based on this rule over here, right? How about scientific to standard? So let's try 6.73 times 10 raised to 4. So we have 6.73 over here. We want to keep moving this point until we moved it 4 times to the right this time. Because remember, we move it to the left if it's converting. So it's vice versa, basically. 1, 2, 3, 4. And then, by the way, make sure to fill up any gaps with zeros. So it becomes 67,300. Meanwhile, if it's a negative exponent, let's try 3.9 times 10 raised to negative, let's try 3. So once again, we put 3.9, and then this time we move it to the left. So we put 1, 2, 3. Then we put it here and here. And then make sure to put another 0 here because it will just be 0.0039. And then, yeah, just fill in another 0 there. So that's how you convert from scientific to standard and vice versa. Next is fundamental units of measurement. So it's quite a lot, but I'll just try to make it as simple as possible. We have the fundamental unit of measurements, and we have to know what are measured values. There are 3 parts of measured values. The numerical value, in this case is 33. The unit of measurement, which in this case is grams, and the amount of the name of the substance, which is plutonium. This is how you state your given in problem solving. You put the 33 grams plutonium or 22 ounces of coffee, something like that. Measurements can always be derived or fundamental. Fundamental is used by measuring tools such as multimeters, rulers, tape measures, graduated cylinders, any lab equipment. Triple beam balance, we can count that as well. Derive uses a formula such as Pythagorean theorem for area or length times width times height for volume. Fundamental units. There are seven of them. So first is length, which is the distance between 2 points. That will be meters or m, lowercase m. Mass is the amount of material in object and can be represented in grams or g, lowercase g. Time is the interval between 2 points. Interval, not distance. Interval between 2 points, which is seconds or s, lowercase s for your information. Electric current is the flow of electrons and can be called as amperes or capital A. Luminous intensity, but I just shorten it to luminosity, is just the amount of illumination of an object has given, which can be expressed as candela or lowercase cd. Number of moles is the amount of substance but expressed in moles. It's just mole, the word, or mol for shortened. Lastly is the temperature. It's how hot and cold an object is. It can be expressed as Kelvin or K. Now let's take a look at derived units. Now there's not really units for this, but it's more of concepts. You got area, which is a region's surface size. Volume, which is the space occupied by an object. Density, the amount of mass per unit of volume. Speed, the amount of distance traveled with the unit per time. And force, the amount of the force per unit of an area. We usually use the metric system, which is adopted worldwide except in 3 countries. It's now been evolved to be called the International System of Units, or SI. It used decimalization, prefixes, and standard defined in terms of an invariable physical measure. Sorry about that. This is the prefix system. As you can see, you can just pause to analyze it for a minute here, because we'll be using this in the 4th topic, which is conversion of units, and I'll show that later because I've run out of space. But this is so far our mathematical skills in chemistry. Feel free to screenshot, although it will definitely be low quality because of the small text. The 4th and final mathematical skill in chemistry is the conversion of units. So we'll have to memorize or at least familiarize ourselves with three things to note here. So you have first the prefixes. This will be very handy, and as well the letters as well. Might as well memorize them as well. I don't know how to describe the unit for micro. It's like a U, but it isn't. Anyway, here are the 2 formulas, and it depends on the situation what we're going to do. So let's apply our formulas here. First, convert 7 grams into kilograms. So based on we're going to be using for the first 2 problems this one. So to check if we're gonna use that, we're gonna have to do this. We need to convert grams to kilograms. So from grams to kilograms, let's do this blue line. So grams to kilograms. So we're going here, right? We never really cross this red line because once you have to convert something like, let's say, kilo to milli, that's when we have to do an extra step because it crosses by the base unit and we have to do something else first. But in this case, we don't have to do this. So 7 grams to kilograms. So you can just substitute given unit and desired unit. So as we could see over here, first we see the conversion factor. We know that 1 kilogram is equal to 10 raised to 3 grams because that's just the base unit. See? You can just subtract the numbers here. So 3 minus 0 is 3. Just like how 1 megameter is equal to 10 raised to 3 kilometers because 6 minus 3 is 3. So that's very simple. So we now know that 1 kilogram is 10 raised to 3 grams, so we can just substitute here. So that's our given unit, right? And then we just put the conversion factor here. So we have the desired unit and the given unit again, but this time it's in the conversion format. So 10 raised to 3 grams, and then you get 1 times 10 to the negative 3 when you simplify this one, or when you just multiply it, it becomes 7, and then multiply it by this, it gets 0.07. So to type this in the calculator, you really just have to really ignore the what do you call these, the units. So we just put 7 and then in parentheses 1 divided by 10 raised to 3. And then if we put that in the calculator, so I'm just going to do it right now. 7 in parentheses 1 divided by 10 raised to 3 close parentheses, you'll get the same answer but in scientific notation, which is 7 times 10 raised to negative 3. And that's just the same thing here. Now that you know how to convert the units, we're going to try again. So 924 centimeters to meters is actually 9.24 meters, but I'll explain how I get it. So our given is 924 centimeters. So that's 924. And then we put our first desired unit. So that's 1, using our conversion factor, of course, 1 meter. So 1 divided by how many centimeters are there in a meter? 10 raised to 2. Why? Because meter to centimeter, as you can see, it's just 2, as we can see over here. So there are 100 centimeters in a meter, because negative 2. So actually, a tip as well, you might as well just remove these negatives. So just treat it as 10 raised to 2, because in the later solutions, we're going to have to disregard the negative sign. So you might as well start doing that as early as now. So 10 raised to 2. So we type that in our calculator. So we put 924 in parentheses, 1 divided by 10 raised to 2 is equal to the same thing, which is 9.24. So yeah, you just really disregard the units. How about once we have to cross first? How about we want to convert 0.45, let's put a number 3 first. 0.45 kiloseconds, to milliseconds. We're gonna have to do a bit of visualizing here. So from kiloseconds to milliseconds, that's a jump of 6, because as you can see, so 3 to 0, that's 3 to 0 is 3, and then 0 to negative 3 is another 3. So the difference is 10 raised to 6. But we crossed by the base unit, and we have to convert to the base unit first. This is where we get our second, which is just given unit, and then base unit over given unit, and then desired unit over base unit is equal to desired unit. It's a little bit overwhelming, but let's just copy that formula. Remember, given unit is equal to the base unit over the given unit, multiplied again by the desired unit, given base unit again, and then is equal to your desired unit. So let's visualize this. So 0.45 kiloseconds, so just ks, and then we put this over here. So let's ask ourselves, what's the difference between a kilosecond and the base unit? As we could see, it's 10 raised to 3. So we put it back down here. So our given unit is base unit is 10 raised to 3 seconds, but we're not going to put that yet. And then that's equal to 1 kilosecond. So I'm just going to say it in red text. And then we're not yet done yet. We need to now convert the base unit into the even smaller millisecond unit, which is below the base unit. So once again, we can just copy the 10 to the power 3 here, seconds. And then how many milliseconds? So that's just 1 millisecond here, right? Oh, no, sorry. I mixed it up, sorry. This is 10 raised to 3. This is just 1 second is equal to 10 raised to 3 milliseconds. Remember, the reason why we do this is because, just think about it. How many milliseconds are there in a second? There, so there's, yeah, here we go. So there's none, and then 10 raised to negative 3. That's why we do that. And then how to plug it into our calculator is we're going to put 0.45 in parentheses 10 raised to 3 divided by 1, close parentheses, and then 10 raised to 3 divided by 1, close parentheses, is equal to your answer. So that's how you just notate it down. Let's put it in again. So 0.45 in parentheses 10 raised to 3 divided by 1, close parentheses, 10 raised to 3 divided by 1, close parentheses, is equal to 450,000. And that's your answer. So it's a bit confusing, but you'll get the hang of it. So let's keep going and let's keep practicing. Let's convert 135, and finally let's do one last example just for the sake of it. 135.67 watts to megawatts. Well, let's visualize it first. So watts to kilowatts or megawatts is a gap of 10 raised to 6, but we don't cross the red lines, so we don't need to do the more complex format. We can just skip right to the point of substituting. So our given unit is 135.67. Okay, watts. And then we know that our given unit is 10 raised to 6, because our conversion factor, remember, is 10 raised to 6. W is 1 megawatt. So just base it off here. See? 1 megawatt is equal to 10 raised to 6 watts. There we go. And that's just 1. So we're just going to label it for the sake of making it complete. And then just convert it again. Let's put it in our calculator. So I want you to put this in your calculator. I'm just going to write the equation. Hold on. And that should be your answer. So let's put it in your calculator and let's see if we have the same answer. And after you put it in the calculator, it should be equal to this. 1.3567 times 10 to the negative fourth. Or let's convert it to standard notation. So 1.3567. And then based on our rule, we have to go here to the left. So 1, 2, 3, 4. So this is our answer here. This is our answer. So it's pretty long answer. So let me just fix up my 1 real quick. 0.00013567 megawatts is our final answer. So it actually depends on if we should do standard or scientific. It's really based on the question, but just do what is given. And finally, after all that's a lot of math, by the way, so good job if you made it all the way through. We're done with the introduction to chemistry. There's actually there's not gonna be any. You can take a break from the math for now because these all the way up to 1 through 8 contain no calculations whatsoever. Only at number 9 are we gonna calculate stuff. So, good job if you made it this far. You're doing great. Alright, so this took a while, but it's finally done. So next is pure substances versus mixtures. This is actually already covering 3 topics, so we should be almost done after this one. So, pure substances versus mixtures. So let's start with pure substances. These are chemically combined substances, obviously. Over here. However, sorry about that, but yeah, these are chemically combined, which means they're not physically combined like how you mix water and salt. No, they've gone through chemical reaction, and these can exist as one substance, as well as having uniform property and unchanged chemical compositions. These pure substances can be classified as, well, a compound or an element. Sorry, compound. Yeah, compound or element. Please disregard this. I didn't check properly. So it's a compound or an element. Next is mixtures. So these are 2 or more pure substances physically combined, just like I said, water and salt, and then sugar, I guess. But due to this, these have inconsistent properties. As the stuff you add, they're not really consistent, they're not the same. That's why we have inconsistent properties. And of course, these properties change over time, which means when you leave a pizza out, it doesn't stay like that forever. It will change, obviously. That's an example of a mixture. But these can be physically separated. You can get a pizza and separate the cheese, the sauce, the dough, and the toppings as well. And these can be homogeneous and heterogeneous. And just as simple as that, that is already pure substances and mixtures. But let's go to the subcategories of pure substances first. These can either be an element or compound. An element has one type of atom. And of course, these are derived from the periodic table, which means we have 118 known elements. These are classified to metals, nonmetals, or metalloids. Metals can have high conductivity, malleable, thin wires, solid at room temperature except for mercury, which is Hg on the periodic table, and these are shiny. How about nonmetals? Nonmetals, they can be solid, liquid, or gas, and are not restricted to being solid, unlike metals, but these are brittle, low conductivity, and not shiny. Or they lack luster, basically. Anyway, last one is metalloids. They're just a combination of both metals and non-metals. So a good example would be antimony. This is shiny but brittle. You can look it up. It's ANTIMONY. And boron, which is a shiny can conduct but brittle. It can conduct metal, can conduct electricity, which is metal. Shiny, which is metal, but it's brittle. So it's a mix of non-metal and metal properties. Sorry. How about for compounds? Compounds are just multiple types of atoms with different properties. We have the law of definite proportion, which means if you take, in this example, 2 hydrogen atoms and 2 oxygen atoms, you chemically fuse them, you have to end up with 2 water molecules. And yes, a combination of 2 or more atoms is called a molecule as well sometimes. The name is derived from the atoms they compose of. So let's take another example. Sodium, which is Na in the periodic table, and chlorine, which was, I believe, CH in the periodic table. Those are actually salt, or sodium chloride, that's where we get the name salt from, sodium chloride. And the product is different from the atoms it composes of. We know that hydrogen and oxygen is a gas. So, logically speaking, gas plus gas would equal another gas. But we know for a fact that water is not a gas, it's a liquid. The liquid we know of, it could be water vapor. However, in general, it's just liquid. How about our mixtures? We can classify this as homogeneous and heterogeneous. Homogeneous is a single phase of matter, which you can't distinguish the parts. I will illustrate these two later. These have uniform composition, components can be separated physically, and these are called solutions. So let's have a before and after. So let's have this plus this equals this, okay? So we have two beakers containing two solutions. Let's say red, let's say a red substance, just red substance, okay? Plus a, let's say, blue substance. Okay, if we're making this a homogeneous mixture, it would be a purple substance. Once you mix them, it should become a purple substance in this case. So as you could see from this, you can't distinguish where's the red, where's the blue. That's why we put indistinguishable parts there. However, what if we apply the same logic to a heterogeneous mixture? There's actually two more subtypes of heterogeneous mixture. So let's just get this out of the way first. Applying the same logic, well, let's say we have a blue mixture this time, a light blue mixture, and this time let's have a yellow mixture. If we know how to mix colors, we should have a green mixture. However, this would be a heterogeneous mixture, so it actually means that you can physically see the blue and yellow mixture together. However, this is actually called, there are two types of this, a colloid and a suspension. This is a suspension, the one I just drew here, suspension. Because as you could see, they're suspended on top of each other. They're just layered, stacked on top of each other. Let's just say the blue is water and the yellow is oil. So that's the best example of a suspension. However, let's try the same thing again. This time with a green. Let's try again with a blue and yellow substance, shall we? So a blue and yellow substance. Let's see. Let's just put, a little bit, Just put a little bit now, and then let's just fill up the blue cup. And then this will still make a mixture, obviously. But this time, in this case, we make a different type of heterogeneous mixture. So we got the blue here, and it's mostly blue. However, there are yellow bits, because remember, we still cannot physically mix these, and that's why this is called a colloid. They're just little bits of yellow there. They're just suspended in there. It's somewhat like paint. When you try to mix paint, you still see a bit of dyes. Yeah, it's something like that. So yes, this is the difference between pure substances and mixtures, as well as elements and compounds, and the two different types of mixtures. And yes, with that out of the way, we can tick off this, all of this. Feels satisfying once we've completed most of it, I'm just gonna tick it properly, so that's more there, and might as well clean it up a bit here. And yeah, with that out of the way, we actually only have two more topics. Yeah, there's only two more topics to discuss, and I will just add the number 6, techniques in separating mixtures, underneath here. We still have a lot of space, so let me just prepare. So these are the 5 technically techniques in separating mixtures. So let's get started. Filtration is basically you're filtering these two components here. So we have solid, these can be used for solid liquid mixtures. It involves the filter paper, as you can see here. I illustrated it in yellow. And then solids filtered are residue, so I've made that one orange. And the liquids filtered out are filtrate, so I made that purple or pink. And then as you can see, we got a mixture here. We got a funnel, filter paper, residue, and filtrate. So you just pour in the mixture there, and the filter paper will filter everything. And yeah, this is probably one of the common ways on... Actually, all of these are pretty common ways on how to separate mixtures. I think I've seen them before. Second is evaporation. We did this in one of our lab activities, okay? So we put a salt water mixture, and as you can see, we rely on the differences in boiling point here, because if we're having like a mixture of some sorts, we have a lot of different elements and compounds with different boiling points, and of course the element or compound with the lowest boiling point will boil first here. So in this case, it's water, and then you're left with salt. So unfortunately, the downside of this is you're only recovering the salt. You lose the water in the process, which really sucks, honestly. It relies on the heat from a Bunsen burner, and it relies on an evaporating dish to keep it, keep it steady, so that the container itself will not break, because glass actually might break it under heat. So we use evaporating dish instead. The third one is distillation. It's a solid liquid or liquid liquid mixtures that can be used here. And once again, it's almost similar to evaporation. It relies on heat, but you can recover both components here. As you could see over here, we have a thermometer over there. That's the red thing. You got the burner again, and you got the filter. I don't know what's this pipe called, connecting them to, but yeah, that's how distillation works. And fourth, last but not the least, is the magnetic separation. So this is used in solid mixtures, and if one of the components in the mixture is magnetic, it's obviously not going to work if both of your components are non-magnetic. It's not gonna work because you need a magnet, and it will not separate anything. So it relies on the magnetic properties of one of the two what do you call this? One of the two components. And that right there is this techniques in separating mixtures mostly. However, there is one I haven't drawn here called chromatography. Unfortunately, I just don't know how to explain this really. It's pretty complex, but you can look it up. Chromatography. Yeah, after this, we're almost done. We literally have one more topic to go. I'm going to show you the types of solutions, how the factors can affect the solubility of a solution, and how can we express the concentration of a solution. So let's start. Solutions are just homogeneous mixtures, which means you can't tell apart the elements that are in there because they're homogeneous, but they are made out of two or more pure substances or elements. They also do have a uniform and consistent composition throughout the sample. Solutions are made out of two things, the solute and the solvent. So let's start with the solute. The solute is dissolved in the solution and thus is typically in the lesser amount. Because it's typically in the lesser amount because our values, the values that we put into the solving part we have later, it's usually less than 100%. How about the solvent? So it's used to dissolve the solute and thus is typically in the larger amount. We'll see the solute and the solvent in action in our problem solving later. Let's go now to the types of solution. Let's base it off their phases. So you don't really need to memorize all of this. It's quite a lot, but you just need to make sure you can differentiate which is a solid, liquid, and gaseous solution. So a solid solution, let's give an example. So a gas solute and a solid solvent will make a solid solution, which in this case is hydrogen in palladium. Palladium is an element in the periodic table, and it's just a type of metal. So yeah, we got a gas, hydrogen, and a metal, palladium. Same thing here, with a solute liquid and a solvent solid. We have liquid mercury, because it's in room temperature probably, and solid palladium. That's just going to be a solid solution because the liquid mercury is in negligible amount or small amount only. And the best example for a solid solute and a solid solvent is steel, because steel isn't an element in the periodic table. It's actually a fusion of a lot of other elements. That's why it's actually technically a solution. Next is the liquid solutions, okay? So these solutions are obviously liquid, and I'll show you what is here. So for a gas solute and a liquid solvent is the soda, because there's a lot of carbon dioxide and other stuff. You have the water, you got the flavor and everything. So that's why you get a liquid, and then when you drink a soda, you feel gaseous sometimes. It's because of the gas that's in there, but it's mostly liquid that you drink. Then for our liquid solute and our liquid solvent is rubbing alcohol. This is why you see the 70% solution, because it's not 100% pure alcohol. You dilute the solution. We'll talk more about dilution and concentrated solutions later as well. Lastly, we got the solid solute and the liquid solvent, and that's just salt and water. I think this is pretty self-explanatory why it's considered a liquid solution. Lastly is the gaseous solution. We have the solute here and the solvent over here. So let's take a look. Gas and gas is actually the air in our atmosphere, because the air in our atmosphere is not fully just oxygen, okay? It's actually 75-ish% nitrogen, 20%-ish oxygen, and then a lot of other more chemicals or elements in negligible parts, such as carbon dioxide, which is made like 0.03%. So it's actually the air we breathe is actually a gaseous solution. Liquid solute and gas solvent is just water vapor in air. So yes, this is pretty self-explanatory. Even though technically the water vapor is gas, well, it can be considered as liquid as well. And finally, solid solute and gas solvent is mothball sublimed in air. So these are mothballs, and they kind of disappear or like change phase when you sublime them in air. They eventually dissolve. They're really weird, and I don't really know how to explain them, but all we know is that that's actually an example already of a gaseous solution. So that's really it, really, for the types of solution. You don't really need to memorize all of this. You just need to familiarize on how to identify if a solution is solid, liquid, or gas, as well as the two terms here, solute and solvent. With that, we can already move on to the factors affecting solubility. Okay, so for our next one, I have already written quite a lot, and honestly, it's really just all of this already. It's all of this is written down already, so I just need to do the problem solving for number 3. So let's get started. So there's another way to actually express a type of solution, and that's by its concentration. So it can either be qualitative or quantitative. When we say something is qualitative, it's just descriptive and comparative. So like we use these two words, diluted and concentrated. It's basically comparing two things. Like, oh, Singapore is better than Malaysia. But in this case, oh, this solution is, let's say, more diluted or more concentrated than the other one. Meanwhile, quantitative is just measured numerically. So you will get a fixed value, and from that fixed values, you can tell if it's unsaturated, saturated, or supersaturated. What do I mean by this? So let's first ask ourselves diluted or concentrated. In these illustrations I've seen here, I've drawn here, there's diluted and concentrated. So we have here beaker C, we have 20 grams of salt, and beaker D, which has 5 grams of salt. However, they do contain the same 100 milliliter water. We call the beaker C concentrated because it has the greater solute dissolved. So we can say solution C is more concentrated than solution D. Meanwhile, we call solution D diluted because it has less solute dissolved. So we can say that solution D is more diluted than solution C. So you really just have to look at the numbers here, nothing too special, and then you can just say, okay, this one is more concentrated, this is more diluted, something like that. It's really very simple. How about unsaturated, saturated, and supersaturated? Now, we're measuring numbers here, so we have to look on the given. You'll obviously given the amount of solute, which is 10 grams of salt, the amount of solvent, so that's 100 milliliters of water, and most as well as the temperature here. So you want to analyze these three numbers and check for three things. So in an unsaturated solution, the amount of solvent or solute is clearly less than the max. So as you can see, it's 5 grams here, but as I've stated, the max is 10 grams. And of course, it follows the 100 milliliter water at 20 degrees Celsius. So an unsaturated just contains less than the max amount of solute. How about the saturated one? So same conditions, but this time with 10 grams of salt in the same amount of water at the same temperature. Now, it contains the exact amount of solute, And I'm telling you, it has to be exact. If it's 9.99, it's going to be considered unsaturated. And if it's just 10.01, it's considered supersaturated. So it has to be strictly containing the exact amount of max solute. How about the 25 grams of salt with 100 milliliters of water? Same conditions, but we just have 25 grams of salt. This one's called supersaturated because it contains more than the max amount of solute. It's really not too difficult, and honestly, it's pretty self-explanatory. Just by looking at the terms, you can tell already which one's which. Okay, let's now move on to the factors affecting solubility. Remember that the solubility is the max amount of substance that dissolves in a given amount of solvent. However, this term is actually used for solid liquid solution. So it's going to be called solubility if it's solid liquid. However, for liquid is actually called miscibility. Let me check. Miscibility. So just remember that term. It's pretty ish. Yeah. It's called miscibility. Anyway, what are the factors to consider here? The polarity of the solute is the first one. It refers to how the atoms of a compound are bonded, but we don't really need to look into the atoms because usually it would just be simply stated as polar or non-polar. So we know that like dissolves like and polar dissolves polar. So in this case, if we are given this table, which of the two substances will be making most likely to form a solution? Well, it's obviously solid and liquid A because they're both polar. It's that simple. Just look at the tables. Alright, for temperature, we have a pretty interesting graphs here, but it's not really too hard to recognize. So we know solids in liquids, they dissolve much faster at higher temperatures. So as we could see, we have all these solids in different temperatures. So as we see the temperature goes up, the solubility of all of these also go up. Sometimes the solubility increases by like 5 or 10 times. How about for gases, however? For gases, it's different. It's the exact opposite. As you could see, at 0 degrees Celsius, they're very high solubility here. But at 40 degrees Celsius, as you can see, they're much lower in solubility here. Which means gases dissolve slower at higher temperatures. So if you want to dissolve gases, it has to be in lower temperatures. Probably even negative temperatures, because we can't really see it here. Number 3, pressure. So solids and liquids aren't affected by pressure too much. If you're just making it like from 10 psi to 11 psi, probably not much for solids and liquids. However, if you're going to go for higher pressure, it will eventually dissolve a solid. And as well as higher pressure causes gaseous solutes to be dissolved. This is why when you shake a can, it just pops right open and all the gas comes out because it wants to escape. It's dissolved in the solution and that's why you hear a pop. Lastly, particle size. Smaller particle size dissolves faster due to the surface area coverage is greater. So basically, this is why we crush up sugar cubes before we put them into a beverage. And that's really it. That's just the 4 factors affecting solubility. Next are the formulas to remember, and this is really just the ways of expressing concentrations of solutions, and there's also 2 M's. So molarity, let's start with this one. Molarity is this one right here. So it's just moles of solute divided by liters of solution. Just one thing to note here, it's liters of solution. So if you're given milliliters, you have to convert it. Otherwise, you will just have a ridiculously high or low value, which in turn will just not make sense on paper. So remember, convert to liters. Similarly, molality is the same thing, except it's actually kilograms of solvent instead of liters of solution. Well, once again, for molality here, please convert to kilograms. Please convert to kilograms. That's the only thing about it. And finally, percent by volume and percent by mass. It's just really concerned about how concentrated is the solution in terms of percent. And as you can see, just don't forget about the times 100. And that's really all the formulas we have to remember, and just always take note that the solution is equal to the solute plus solvent's mass or volume or whatever. I'll Well, that's really it, honestly, for all the three topics. I'll show you some problems in a bit, but I'm going to move. So yeah, I'm gonna move on to the problem solving. So just give me a bit to set up. A screenshot if you need to. It's a bit low quality if you try to screenshot. So yeah, just try the screenshot. Science guides. This is going to be a review on 4 topics. So I can't really list it right now because I haven't prepared anything, but this is related to molality and molarity, as well as doing percent by mass and percent by volume. These 4 key concepts are the only ones that will be present in your written work 3, which will be coming up on cycle 7, day 6. So I'm going to be explaining the 5 problems given in these slides today. So yes, I'm going to go in depth and explain how I got each one. So let's start with this first one over here, okay? So we know that we have to write the given first, as always. So we're given 0.247 moles of potassium nitrate. So let's just write that down. I'm gonna be using the shortened version, but that's the same. You just need the number. And then we have 750 liters of water. So these are our 2 given for today and for this problem, and we're gonna have to find the molarity. So in our discussion, this is the most simple basic problem you can get. Simply, the formula for molarity is, so you want to put the moles of whatever solute. Yeah, solute. So you want to put the solute over here. So that's 0.247, that's the value, right? And then you want to put the amount of liters of substance at the bottom. So this is the molarity. You don't really need to put the stuff here because you really only need the numbers. Now you're just gonna plug it into your calculator, and if you put it in the scientific calculator, it actually shows it in scientific notation. So I'm just gonna review on your scientific notation. You put it here, it's going to be 3.293, about like that, and then times 10 to the negative 4th. So we obviously want to change that to standard notation. So what you do is I just put 4 zeros before this number, because that's my technique. I use -4. Then put 3.293. Then, since we want to make the number smaller, we go to the left. So 1, 2, 3, 4. So it becomes 0.0003293. And since we have 4 significant figures here and 3 significant figures here, it's actually okay to put 3 or 4 significant figures. So that's our final answer. So for this one, it's actually 0.0003293 moles per liter. Okay, I'll give you time to screenshot this one, and I'll now move on to the next one. So this is number 2. Okay, once again, we have to always read for the given. So you are preparing a laboratory solution to determine how many moles of sodium hydroxide, NaOH, are present in a 500 milliliter of a 0.42 molarity solution. By the way, capital M means molarity. So I'll just write that down. And strictly, it has to be capital M, because if it's small m, it's molality. So let's give our given. So it's a 500 ml solution, 500.00 ml solution, and a 0.42 moles per liter solution. But we have 500 ml volume. So in our molality formula, we have the molality, so we can put 0.42 moles per liter, and then is equal to, we have our 500 ml of solution. However, it's liters of solution. So recalling back from our conversion, 500 ml is actually equal to 0.5 liters, because 1000 milliliters is equal to 1 liter. So we put 0.5 liter here. That's a common mistake, by the way. We have to convert first to liters, and strictly liters. So as you could see, what's missing is in here, which is the amount of sodium hydroxide. Yep. So how do we find this? We have to do the cross multiplication technique, and we'll replace it with x. So the cross multiplication technique, you put on this other side, you disregard the unit first, and just put 1 is equal to, copy this, so just x is 0.5. So you should have something like this. Okay, let's cross multiply. 1 times x is equal to 1x, or if you know what the basic rules of math, is just x. And then we do 0.42 times 0.5. That will mean x is equal to 0.21. You put that in your calculator. 0.5 times 0.42. Now, that's your answer, because in some cases we actually get a decimal. We have to get a decimal for x, but not in this case. So the answer is 0.21 moles of sodium hydroxide, or we can just express it as NaHO. Oh, my bad. OH. So take note of the steps. We first represent, cross multiply, then find the answer. 3 steps only. Take a screenshot, and we're gonna move on to the third one. Okay. So this one is now about molality. How do I know that? It's because we have kilograms in the question. See? Kilograms. And in the previous questions, we have ml. We have milliliters. But now it's kilograms. So the formula actually isn't much different. So let's first take the given. We have 0.380 moles of potassium chloride, or just KCl. And we have 0.71 lower m, which means molality. Remember, capital M is molarity and lower m is molality. So we can do this, it's just mole per kilogram. Let's visualize that. So the molality formula is going to be kilograms of solution and over the amount of solute. So it's very simple. It's very similar. Wait. Okay, sorry. Solvent. Sorry, I'm a bit tired, okay? Moles of solute over moles of solvent is equal, over kilograms of solvent. Kilograms of solvent is equal to your molality. Okay, let's visualize this, okay? So do we have our molality? Yes, we do. So it's 0.71. Now let's question ourselves. Do we have the moles of solute. This is solute. Moles of solute. Do we have that? We have the amount of moles of solute there. So we can just put 0.380 here. What we don't have is the kilogram or the solvent of water. So we don't know what this one is, and we can replace it with X. And this one is actually even more simpler than the other one because we don't need to cross multiply for this one. We actually need to divide this time. So what you want to do is, okay, you do not want to get this mixed up, is that we want to divide the moles of solute by the molality, just the raw values. So you will get 0.38 divided by 0.71. Once you plug that into your calculator, it's equal to about 0.535. And then you already have your answer. That's going to be 0.535 kilograms of water. Take a moment to take a screenshot. If you have any questions, just don't hesitate and I will explain each bar. Alright, let's now go to the fourth one. So the fourth one is now about the volume, the percent by volume now. So let's do this. So the given is that 10 ml of glycerol and 250 ml solution. So how do we calculate for the percent by volume? So it's very easy. Percent by volume is equal to the volume of the solute over vol of solution times 100. So we actually aren't missing anything. I mean, we have our solute, which is the 10 milliliters of glycerol, and we have the solution as well, so that's 250. So there's really nothing much to solve for or substitute here. You really just have to evaluate this. So 10 over 250 is equal to, once you put it in the calculator, it's actually 0.04. Now we just have to times this by 100, and that's equal to 4. And that right there, you just have to add a percentage, and that's your answer. That's for number 4. Please take a screenshot and don't hesitate to contact me for any questions. Last one is number 5. So let's erase everything once more. So this is probably the hardest one, but so I will write the formula for you. So the formula to use here, given first. Given, we always start with the given, everybody. So it has 15% mass by volume. Percent by mass. And then we also are given 200 grams for the solution. So it's very similar to the percent by volume formula. So it's actually percent of mass is equal to mass of solute over the mass of solution. And as always, times by 100. So this time when we visualize it, do we have the percent by mass? Yes, we have 15% by mass. Do we have the mass of solution? Yes, we do. That's 200 grams. But what do we do now? We're missing x, which is our mass of solute. Once again, we're going to need to cross multiply. First, we need to change this percentage into a decimal. So it's actually going to be just like this. So 15, and then you want to add 2 decimal points. So it's right here, 1, 2. So it becomes 0.15. And like always, on this side where there's no fraction, just put 1. Is equal to x over 200. Now you can just cross multiply. 1 times x is just x, or 1x. Is equal, and this is equal to 0.15 times 200. And that's just 30. And there you have it. Your answer is already there. So it's 30 grams of sugar. Feel free to take a screenshot. And that's all for the practice exercise we had this session. I hope I made it a bit more clearer, and I hope you will be able to pass the written work 3 and as well as the ETA. I will be making a guide for the ETA as well. Thank you once again for watching. Please feel free to share this video to anyone who needs it. And yeah, sorry if I sound a bit sick. It's because I am. It's been a tough week indeed. Well, I'll see you guys next time. Bye-bye. So the last topic we'll be discussing for this video is acids and bases. I really didn't have much to work with here because like I only was given as you can see here, based on different tests, the effect of acids and bases and the classification based on their pH. So the pH just means the potential of hydrogen. So basically 14 means, I think, yeah, 14 means like very little, very low amount potential of hydrogen. Then 0 is basically like hydrogens everywhere, or like basically like that. I can't really say for certain, so we have to review the material because I was actually absent during this presentation because I was sick. However, I do notice a pattern here. So we see that acids. For acids, just refer it to color red, and it will turn anything else other than the phenolphthalein to red. So as you can see here, it turns the blue litmus paper to red, and of course, since red litmus paper is already red, it would have no change. With the grape juice, it also turns red. So if you see this characteristics and colorless, it's most likely an acid, because just associate acid with these warm colors here, red. Same logic really for blue. So like as you could see, it just turns everything blue except the final chemical, which turns red. See, blue litmus paper is already blue, thus there's no change. And red litmus paper is not yet blue, so it will turn it blue. With the grape juice, it turns it dark green or dark blue, which you can associate with the colors for alkali or weak and strong bases. And lastly, it just turns the last color to red, okay? So if you're stuck with this one, it's colorless or red. So yeah, it's not really much to work with, honestly. You really just have to check which is the correct one, which is the correct properties to deal with. But yeah, this means we've completed the entirety of this competencies, and honestly, this is my longest guide ever. It's the most amount of effort I've worked with, and I'm really proud of myself for making it this far. I recorded for a good, basically the entire day, but I did make sure to, make sure I was still getting some rest, not overworking myself. I'm still in the process of working myself. working myself out, because I know I have a lot of flaws, and like I know I'm very much aware of that, and I'm working on them. That's why I'm trying to be like more optimistic when it comes to guides. And yeah, I just I just study when I want to, and like I'm disciplined enough. I know I'm disciplined enough to know when is that time. I don't study because I need to. I study because I want to. And that's the reason why I'm able to make guides this long, because when I'm recording, I'm genuinely wanting to help anyone. And yeah, I just hmm, I'm just trying to remove any, like, worries about. I'm trying to de-stress myself, and hopefully hopefully you aren't too stressed about the ETA, because remember, in the end, this is from my English teacher, and in the end, grades are just grades. Like, they don't define you. Great. I definitely also agree with my another teacher, my Filipino teacher from 2 years ago. I remember him saying that, yeah, grades don't define. They matter, but they don't define you, which is the point. I hope this update on me ensures that I'm not overworked. And honestly, I'd do another guide if I had the time, but it's just I just have to wake up early. All in all, I'm a school bus rider. I have to wake up at like 4:30. But yeah, I hope you understand, and I really, really, genuinely thank you so much if you made it all the way to the end here. And yeah, if you made it all the way to the end, you absolutely deserve to know how I'm doing. And like, honestly, your support is incredible, and it's one of the reasons why I keep going. So yeah, once again, thank you so so much for sticking with me for almost 1.5 hours. I really genuinely hope you get the score you want. You'll be happy with your score. And once again, as always, I'll see you in the next one. Bye bye.